So far we were talking about integers, and when I said integers I actually meant only positive numbers, right? Of course I included 0, so you could say that it's just the whole numbers, so to say, right? 0, 1, 2, 3 and so on. But the fact of the matter is we know that negative numbers are useful in many contexts, right? And the problem as far as binary is concerned is once again notation, right? I don't have a separate minus symbol that I can use in order to indicate that the number is negative. I have only 0 and 1. So what do I do, right? We have already come to the conclusion that maybe I'm going to use 8 bits or 16 bits, a fixed number of bits in order to represent a number. Now I'm proposing another convention which says that let's say let's look at the most significant bit, and if that value is equal to 1, I will say that this number is negative, and if that value is 0, I will say that the number is positive, right? In other words, I use the convention of location, right? The most significant bit, I treat it as a minus sign rather than as a place value. Okay, does this work? Yes, I can of course represent numbers this way. So effectively what would happen is that the number 0, 0, 1, 1 for example would have the value 3, and 1, 0, 1, 1 would have the value minus 3. Okay, now what you need to keep in mind, for example, is then what is the value 1, 1, 0, 1, 1, right? Is it equal to 27 as we saw earlier, or is it equal to minus, in this case this is 8 plus 2 plus 1, so that's 11. Which one of these is it, right? So this is essentially the question that immediately pops up when I see something of this sort. The answer is actually fairly simple. If I know that my convention is to use signed, the sign bit, the most significant bit as the sign, and my convention is that my numbers are 5 bits wide, then this is correct and this is wrong. Okay, it's as simple as that. It's convention, right? I have just told you that I am using a signed representation where the most significant bit indicates the sign, and that my numbers are 5 bits wide. If so, then this value 11011 is minus 11. It is not 27 in that context. That is the power of convention, right? That you need to keep in mind when you are looking at how to interpret different numbers. So with that convention in mind, what I'm sort of implicitly assuming over here is that these are 4-bit values, right? And they have the sign bit. So once I make those two assumptions, then I can confidently say that this is equal to 3 and this is equal to minus 3. Okay. Now the question of course is, I need to know how many bits I am going to use, right? And that is so that I interpret it correctly. It also means that I can extend if needed. What I mean by extend is, let's say that I am trying to represent the value 3. I know that 1, 1 corresponds to 3, but I also have to be told that hey, this is a 4-bit value, so yes, I extend it out to 0, 0, 1, 1. And if it is minus 3, I say that 1, 1 corresponds to this. The MSB should be equal to 1 to indicate a negative number, and therefore I have 1, 0, 1, 1. Okay. This kind of notation is called signed magnitude notation, right? And there are contexts in which it is actually used. Okay. But there's a bit of a problem there, right? One issue with signed magnitude, right, is that if I have an n-bit value, right, and I'm dealing only with positive numbers, we already know that I can go up from 0 up to 2 to the power of n minus 1, right? So for example, for 8-bit values, I can go from 0 up to 2 power 8 minus 1, 255. Let's say that I use 1 bit for the sign. Okay. Now what happens is, I effectively have two ranges, right? So this part out here corresponds to the positive range, where I have from 0, 0, 0, 0, etc. up to plus 127, right, which basically corresponds to 0 followed by all ones. Okay. So far so good. The problem is, look at this number out here, right? I have all of these, the value bits as 0, but there is a 1 in the sign place. So effectively what it's representing is a minus 0. Okay. minus 0 is the same as 0. So effectively I have two representations for this particular number out here, right, and I can go up to minus 127. So that part of it is okay, right. I end up with a redundant representation for 0, okay. Now there are a couple of other problems with the signed magnitude format. The main issue actually comes when we try to do arithmetic with signed magnitude, right. If I want to take a number and convert it to minus of that number, it's actually very easy. I just sort of flip one bit, nothing else. But if I want to subtract two numbers, 10 minus 3 for example, right, I have to take 3, I have to take 10, I flip 3 to make it negative, and then I need to have an explicit subtractor circuit, right, which allows me to actually do the subtraction. It turns out that in practice there is a slightly better solution, right, which uses something called a complement notation, right. And what exactly do we mean by a complement? I'll be defining that in a moment, right. So what we say is, if the number is positive, it's greater than or equal to 0, I'm just going to store x as a regular binary number. But if it is less than 0, what I'm going to do is store something that I call the complement of the number, okay. And in this case what I'm going to do is that I'm going to define this complement as essentially the value 2 to the power of n minus 1 minus the magnitude of x, okay. So in other words, what will happen is, if I have a value 17, then I will actually take 2 to the power, and if I want to represent it as an 8-bit value, I'll take 2 power 8 minus 17 and represent that, okay. We'll get to an example in a moment, but effectively in terms of the number line, what is happening over there is, I will end up having a representation for these numbers minus 128 to minus 1 will all be treated as negative numbers, and I have to take their complement if I want to represent them. But the numbers 0 up to plus 127 are treated as positive and will just stay as they are in binary, right. So what does this complement mean over here? What I will do is, I will take these and map them. So this minus 128 will get mapped to the number plus 128, the number minus 1 will get mapped onto the number plus 255, right. Effectively this whole region out here, this part of the number line, is going to be picked up and moved over here, right, so that these values get mapped correspondingly over here. By the way, one minor correction, this should actually be 2 to the power of n, not n minus 1, right. We'll get to that in a moment. So let's take an example, right. With n equal to 8, we know that the number plus 17 can be represented as 0001, 0001, right. This is basically equal to 16 plus 1, that's how I get 17. So this representation is unambiguous, right. I know exactly what it means. The most significant bit happens to be 0, right. So there is no question of whether it's a negative number and so on. This is perfect, it's okay, right. If I want to do minus 17, right, if it was signed magnitude, what I would have done is, I would have flipped this bit to 1 and just stopped there. But here what I'm saying is, I'm going to do something slightly different. I'll actually take 2 to the power of 8 minus 17, find out that that value is 239 and get the representation of that out here. This is the binary representation of 239. You'll notice that these two don't seem to have any connection, right. That's not strictly true. There is in fact a neat way of going from one to the other, right, which we'll look at more probably in the exercises, right. But there is a pattern out here, right. More importantly, this notation out here helps us with certain kinds of computations, right. In particular, what ends up happening is that this 2 power 8 minus 17 makes it much easier for us to do certain operations such as subtraction, right. In particular, if I want to subtract a number, I basically take the 2's complement and add the result, which means that I have now converted the problem of subtraction into a problem of complementing and then addition, and the complementing turns out to be something that I can implement very efficiently in hardware, okay. So let's look at a few numbers represented using this notation, right. So this kind of notation is called 2's complement. Again, it's a convention. unless I tell you that these 8 bits are being represented using 2's complement format, you don't really know how to interpret them, right? Now, one thing to keep in mind, if I tell you that this is a number in 2's complement format, that's it, this is the number, and the question that I'm asking basically is, what does this correspond to? And the answer is plus 17. Okay, there are a number of scenarios where I've seen people saying that, okay, the moment I say, okay, this is a number in 2's complement format, they decide to take the 2's complement. No, that's not what you need to do. 2's complement is a representation, right? If I tell you that this is a number in 2's complement format, it only helps you with interpreting the number. It's not immediately telling you that you need to take the complement of the value. The complement itself is just this operation. Okay, so please keep that in mind. Now, plus 127, right, 0 followed by all ones, happens to be the largest positive value that can be represented using this approach. Minus 128, which is 1 followed by all zeros, is the most negative value that can be represented. Okay, so these are sort of a little bit about what are the kinds of numbers that can be represented with 2's complement. Once again, I am not going to go too deep into 2's complement arithmetic or how it is implemented or how it in turn influences the design of digital hardware. That is actually better addressed in a course on digital logic. Okay, what you need to know as a programmer is certain things with regard to what it actually implies, right? Now, there are a few things that happen. One is that there is no redundant zero, so that problem from signed magnitude is at least taken care of. It covers the full range of available numbers. For 8 bits, there are actually 256 different numbers that can be represented. It turns out that in hardware it's easy to compute, right? The algorithm is actually very trivial. It basically says invert all the bits and add 1, right? Once again, right now in this I'm not going to go deeper into that, but it's something that you would probably need to know in the courses that you are going forward with. The one big advantage of 2's complement is that it actually makes arithmetic easy. Once again, as a programmer you probably don't care, but as someone who is using a computer, and if at some point you do get into the design of a computer, you probably should understand that addition and subtraction now become identical operations, and therefore it has a significant impact on how they get evaluated. This is not part of the C language specification, right? So you don't, strictly speaking, need to know or care about how numbers are represented as negative numbers when you are writing a program in C, right? But having said that, it is relevant enough in the context of embedded systems and so on that knowing this notation has implications for how you interpret numbers later, right? Especially when you start seeing numbers with 1 in the most significant bit and so on, you need to understand how that might have arisen, the fact that they represent negative numbers, and in turn are you able to sort of interpret those. All of those are useful skills to have. Now, we have looked at both positive and negative numbers represented in binary, and binary is fundamentally difficult for humans to read, right? So even for a number just as simple as 91 or something, I have a 8-bit representation out here, right? So it doesn't, ideally if this was an 8-digit decimal number, then I might start think in terms of 1,011,011 and so on. Yes, I at least have a way of verbalizing it. I can't do that with binary, right? I just literally have to say 0101 1011, right? And hopefully not make a mistake while saying all of this, right? It's clearly not meant for humans, right? It's directed more at the computer. But we as programmers are going to be interacting with the computer a lot, right? We could try and have all of our values being written in decimal, but there are a lot of things, especially in terms of the range of addresses, the size of arrays, the size of different data structures and so on, which it turns out that having them in binary makes it much easier to understand how the memory is being used. Okay, so then we'll have to keep switching back and forth between binary and decimal, and the decimal equivalents of many of the interesting binary numbers are just horrendous, right? I mean, they are not easy to remember at all, right? So for example, what is 2 to the power of 32 minus 1, right? In decimal it turns out to be some 10-digit number, right, which is not very pleasant to try and remember, okay. But it turns out to be very important in a number of different contexts, especially when you are doing like memory maps and so on as far as the computer is concerned. So as the alternative, what we do is we bring in hexadecimal, right? What is hexadecimal? It basically says that, look, this number is using 2 as the base, this number is using 10 as the base. There was nothing restricting you from, using any other base, and in particular I am going to try and work with base 16, right? Why 16? Because 16 is equal to 2 to the power of 4, right, which means that one digit in base 16 is exactly 4 bits, right? The number of different digits that I need to work with hexadecimal is 0, 1, 2, 3 up to 9, and then I need 6 more because I can go up to 0 up to 15. 15 is a single digit in hexadecimal, okay. So this is an exact representation, and what that in turn means is that, for example, if I have 0, 1, 0, 1 in binary, then I know that it is all the number 5 in decimal, it is also the number 5 in hexadecimal, okay. So far so good. What about 1001? That is the number 9 in decimal, also the number 9 in hexadecimal. But the moment I go to 1010, decimal starts getting complicated. I need 2 digits. I have to represent it as 10, right? In particular, what that means is if I am trying to sort of take this and do some kind of changing from binary to decimal or decimal to binary, this becomes a problem because I now need to go over to the next digit. In hexa, right, it just remains as the next digit out there, which is A, right. So I am going to use the symbols A, B, C, D, E, F in order to represent the numbers 10, 11, 12, 13, 14, 15, right. 1101 is 13 in decimal, D in hexadecimal, okay. So this sort of already gives us a clue about why hexadecimal or just hex notation, right, might be useful for us, right. And yeah, where that really shines is when we start taking larger values. So for example, 8-bit binary values, right, if I want to take it and convert it into decimal, yes, I can do that. I will end up getting a value 17, but in hex it's very easy. I just take 4 bits at a time, and that becomes this LSB. The next 4 bits becomes the next digit out here. What about 01011011? It's 91 in decimal, but in hex what do? I just group them 4 at a time and say this corresponds to B, this corresponds to 5, it's the value 5B in hex, okay. So sort of effectively it is a much more compact version of binary. That's essentially why it's useful, right. It helps to sort of bridge that gap between humans and the computer. The computer needs to sort of have things in binary. Humans can't read or write binary easily. So instead we come with a shorthand notation which helps us to sort of bridge that gap, and hex does a good job of that, right. So as a programmer, it's generally a good idea to have a working understanding of hex notation, right. In particular, there will be a lot of common symbols, right. So for example, 0x00 is 0, 0xff, right. What is f? It corresponds to the number 15, but more importantly it corresponds to the binary 1111. So ff basically is all ones over here, which is why you will see these terms where you have ff and so on very often when talking about different kinds of binary. It effectively refers to the largest value that can be stored in some number of bits, right. Notation, 0x is always used as a prefix to indicate that what follows is a hexadecimal value. It's similar to this notation out here where I put parenthesis and a subscript of 16. I can't really do subscripts and so on when I'm normally typing in a computer, so 0x turns out to be more convenient. and F in this case is sort of like the equivalent of 9 in decimal, right? When I have 99999, I'm sort of indicating, hey, this is a big number. The same way in hexa, I would say FFFF, right, to indicate that this is the last number. After that, you are basically rolling over into, needing one more bit for something. So what that means is I can take it further. If I have 16-bit values, the range of values I can represent is from 0000 up to 0xFFFF, right, which is actually 2 to the power of 16 minus 1 and has this value 65,535. Some of these numbers, the more programming that you do, will become familiar to you, right? You don't need to memorize them now, but it's probably convenient, if you are going to do a lot of programming. Same way with 32-bit numbers, they go from this up to FFFF, right? 8 Fs basically. And now the interesting thing is I can also have this notation with 2's complement. I can basically say that anything in the range 0x00, 8 zeros up to 7 followed by 7 Fs, right? Why 7? Because 7 corresponds to the number 0111 in binary. So if I have a 7 over here in my hex, it basically means that the most significant bit is actually 0. Everything else is a 1. So this value, this 7 followed by 7 Fs, is the most positive 32-bit value that I can have. What happens when I add 1 to that? I basically flip it over, it goes, this essentially corresponds to a 1 in the most significant bit and all zeros after that. And I have, the all Fs, right, which actually in 2's complement corresponds to the integer value minus 1. Okay. So effectively, the only thing that you need to take away from all of this is a nice shorthand for long binary symbol notations. Okay, so let's sort of summarize where we are with regard to integers, right? The first thing is that in order to represent integers inside a computer, we probably should be using a fixed width, right? That's preferable. It could be dependent on the CPU or possibly even on the language. As a programmer, what do you need to know? You need to know certain limitations. The fact that, for example, 8-bit integers means that the range of numbers that you have is very small. It's only 0 up to 255. If it's 2's complement, then it will be minus 128 to plus 127, right? Maybe enough for a lot of tasks, quite possibly not going to be enough for more complicated kind of computations, right? Even if I want to add 10,000 numbers, I can't do that because I don't have the range to represent that kind of size. Negative numbers, once again, convention, right? The 2's complement approach is the preferred one in most computers. It's mostly handled by hardware. The only thing that you as a programmer need to know are where it could affect you, for example, when you interpret numbers, or for example, when you add numbers or subtract them and you start seeing overflow, right? That basically what happens to a number that dramatically changes. You expect that 4 billion something plus 100 should give you 4 billion and 100, but suddenly it gives you something negative instead, right? Where did that happen? How did that happen? Where did that come from? All that happens because of the way that these numbers are represented. And finally, hex is a useful intermediate for human and computer interaction, right? Computers prefer binary, or rather need binary, right? Whereas humans prefer to have some slightly more compact representations. This is especially useful for people who are likely to go into embedded system programming, because there you actually need to keep very careful track of the memory usage, and you might also be interfacing with other external peripherals.